Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 4, Electricity and Magnetism, Inquiry Question 2, Electric Circuits, with a particular focus on these following dot points, electric current in metals, and also the current and voltage relationships. This will be split into two videos, just because of the length that this might end up being. So to start ourselves off, we're going to just go through textbook references, as always, is those numbers there. We are going to investigate the flow of charged particles in conductors and wires, and hopefully by the end of the lesson, we can analyze quantitatively, the current and voltage relationship in terms of Ohm's law. Alright, so the first thing we need to talk about is what is electric current. Now, in the syllabus dot point, it also wants you to investigate the flow of electric current in metals and also apply models to represent current. So that's what we're going to try and do. Firstly, let's explain what is an electric current. So, in physics, what we define as an electric current is the movement of charged particles from one place to another. Passing through, that could be charged particles passing through two particular points in a particular time interval. So what we have in this diagram here is our charged particles. You can see the positives and negative charges. So at the top here, that's if we have a positive current, and here's if we have the negative current. Now, although I say positive or negative current, it doesn't actually really matter. In terms of an electric current, we're talking about just charged particles. So when we're talking about charged particles flowing, we need both positive and also negative charges flowing. Obviously, they're going to move in opposite directions. So as you see with our positive charges at the top here, it's moving to the right-hand side. For our negative current or negative charge, it's going to the left-hand side here. Now, what we define as electric current is looking at how much charge is passing through a particular space in a particular time interval. So how many, we could say, electrons, how many positive charges are passing through per second. That's what we mean by electric current. In terms of the basic requirements to produce electricity, we're talking about electric current, that is. You need three things. You need, firstly, charged particles, that being positive or negative, regardless. Technically, you need both. You need a conducting pathway, so it needs to be, a pathway where the charged particles can continuously move. So say, for example, in an electric circuit, you see here, the electrons can move around the pathway in sort of this orientation here. So there's no disconnect occurring here. If I was to cut off one of the wires, you wouldn't get an electric current because there's no additional pathway that the electrons can go through. So there's that. Now, technically speaking, conductors are obviously better at assisting this pathway to go on. What the conductors have is what we call delocalized electrons. So basically electrons that can be displaced into this motion here. Obviously, as we said, also it needs to be a complete pathway. So a broken circuit will not allow for the flow of this electric current. Okay, so this is the formula. I is for current, Q is for the charge, and T is obviously time. So this Q here, it's for the quantity of charge, so how many charged particles do we have? Sometimes you might see it represented as capital Q, so that's what we're talking about here. In terms of the units for current, it is amps. Sometimes we just write just capital A. It's named after the person who actually looked into electric currents, Andre Marie Ampere. So that was his work there, and so to pay homage for his work in electricity, the unit for current is called amps or amperes. If you actually look at the other way of writing the units, we have coulombs per second. Just to give a little context of the different types of current that we have. Now your standard light bulb has about 400 milliamps, so that's 10 to the power minus 3. Your toaster 3 amps, your fan heater 10 amps. You can see that if we compare that to the motor in a car or lightning strikes, it's way higher. So we actually deal with very small currents in our daily lives. And that makes sense because the higher the current, the more dangerous it can be with these flowing charges. Alright, so let's try and model conducting electricity in metal. So we have two types of objects here. On one side we have the metals, which we said are really good conductors, so very good conductor. And on the other side we have an insulating ceramic, so this is a very good insulator. And the way we can work it out is obviously when we have a complete circuit. So we have our switch. When the switch is closed, you can see that on one side our insulating ceramic doesn't have electron flow. On our conductor side though, we have the flow of the electrons or charged particles here. The main thing that's differentiating them is the delocalized electrons. So for the metals, we always say it has delocalized electrons, so it's easily displaced in the pathway, so that's why we see a current flow there. If I was to do a second comparison between that, let's use a paperclip, which is a really good conductor, and then we're going to use a dog. So a dog is a really good insulator. Obviously it doesn't have delocalized electrons. So in this case here we have an insulator here in the dog. We have a paperclip, which is our conductor on this side here. You can see what the conductor is actually doing. It's facilitating the motion of these charged particles to go through. Because it's a conductor, it facilitates that. The dog, on the other hand, is a really good insulator, so it doesn't facilitate, although the dog itself has electrons, it doesn't really facilitate the movement of electrons through it. Now obviously the greater the voltage of the battery, and so if you go to really extreme high voltage, then there is the possibility of charges flowing through the dog, but obviously that's not really practical, and that's why we wouldn't use insulators as a way of being a conductive pathway for electricity. So let's just quickly recap some critical points. Metals are great conductors of electricity, whilst non-metals are really poor conductors, which we call insulators. You can even see the animation here if we compare the wood, which is our insulator, to steel, copper. You can see which ones light up the light bulb. A substance's ability to conduct electricity is based on the amount of detached electrons in the valence shell. So this might be of use for some of the chemists. Now you know that the valence shell is essentially the most outer shell electrons in an atom. So the more easily displaced those electrons are in that valence shell, the more likely it will, be used in a conductive pathway. Okay, so this is a model of a metal ion, and you can see with all metals, the reason why a metal is so tightly bounded together because it forms this thing called a strong metallic bond. And the way it works is these electrons, these valence electrons of these metal ions are just displaced throughout the entire metal lattice. So these negative charges are going to attract to the positive charge, so that's what binds the metal together. But if we're looking at in terms of the physics of metal conducting or conducting metals, these electrons can readily move in between these gaps. So if I put a electric field here, so put in a battery source, I can make one side positive and then one side negative. And once I establish that electric field, that's going to cause these charged particles to move in a particular direction. Once you get moving charges, you get electricity. That's the point, okay? So there's that. I think that kind of explains everything we need to talk about here. Yeah, so the idea is you just need delocalized electrons, and the reason why metals are really good at that is because of their metallic bond structure and the detachment electrons have in their overall structure. So you can see here these are our delocalized electrons. You can see once I put an electric field in, these electrons are now being dragged to the positive end, and these are being dragged to the positive charges get dragged more towards the negative end. So the main point here is metals or conductors in general they're good at or they're good at conducting electricity. Good at conducting electricity. That's because of these delocalized electrons. So once a electric field is added, so when an electric field is added, this actually causes the charged particles to align with the opposite ends. So in this case, if we were talking about a circuit, that could just be connecting the metal with a battery, that will align the charged particles to flow in one direction and that creates our electric current. Okay. Alright, so this is kind of what we're showing here. If we didn't have an electric field, the charged particle is just going to go in no direction. So there's no net movement for an electron originally inside a metal. It's just random. There is no net change in direction, so eventually it'll just be around the same position where they started. And that's why metal won't just randomly conduct electricity when you pick it up. So if you pick up any piece of metal, if it's not attached to some circuit or wire, you wouldn't feel an electric shock because there is no electric current flowing through it. But once you introduce that electric field, that being through a battery or power point or something along the lines of that, we get a concept called electron drift. So the electron is still going to migrate in all these random directions, but overall, the net direction does favor one side of the electric field over another, and that's how we obtain an electric current. There are two types of current flows that we talk about. So I talked about the positive current flow, and then we talked about the electron current flow. So obviously, when we talk about electron current flow, we're talking about negative charges. So negative charges here. And when we talk about the conventional current flow, we're talking about positive charges here. Now, do keep in mind, when we talk about positive charges, it's not the same as saying we're having a flow of protons. The reason being is because obviously protons is inside the nucleus. They don't actually get displaced at all. What's actually happening when we talk about positive charges flowing? It's actually a positive area of space that's being left behind. So imagine you are an electron and you move from this position to this position here. Okay, now let's look at it in the opposite perspective and look at the area that's left behind by the electron as it migrates from here to here. Okay, so let's say this original spot that wasn't occupied by the electron, and then now we compare it when the electron's here. Originally it was sort of more net positive charged. When the electron migrates from the top to the bottom here, that positive charge also migrates here, because where the electron has gone, it's left a positive overall net change, right? Because if you take away a negative charge, then obviously the area around where the negative charge was becomes more positive. So that's actually what we mean by conventional current. It's this flow of positive density relative to the movement of electrons. That's why both of these ideas of electricity is correct. It's the flow of both negative and positive charge. If it was only one and not the other, then you don't actually have an electric current. The other reason being was when we first investigated electric currents, we had this idea of a positive potential or high potential to low potential. So the original concept was the positive end of any circuit was the high potential point, and then any negative point was the low potential point. Now, like we said, now we know the way that electrons flow. We know that it's the movement of the electrons that facilitate the flow of the positive component, but originally that's how we started off with the overall conventional current there, and that's kind of why we sort of stick to it in most of the diagrams here. Another thing you should also keep in mind when we talk about electric currents, when we draw diagrams for batteries, the long end, this end here, is always the positive. The shorter end always represents the negative side. Alright, so if we want to demonstrate the flow of electricity, the electrons are always going to go from the negative terminal to the positive terminal, which makes sense because electrons are negatively charged. It's going to want to move to the positive end of the electric field. The conventional charge, or conventional current, is always going to try and travel to the negative side there. Okay, so what we're seeing here is the flow of electrons. What you'll see is the flow of the positive charge densities left behind by the electrons is going to go in the opposite direction of that. Okay, so that kind of explains everything you need to know in terms of what conventional current is and in comparison to electron flow. Generally speaking, when we talk about current in these calculations here, we are talking about the convention current flow rather than the electron flow there. There are also two types of current flows that we see, and you'll also see in your sort of power supply. One is called DC current, or just DC, which stands for direct current. We also have AC electricity, which stands for alternating current. So you can see in terms of the movement of the charges, you can see that DC is just moving in one direction, and then AC is obviously going backwards and forwards, alternating. So basically following its name. So one direction flow, while as the alternating current changes direction. Okay, so that's what you see here. One way that we can measure how fast the current is flowing is through using an instrument called the ammeter. So the ammeter is placed in series of the circuit, and it helps us measure how much current is flowing over time. If you were to place an ammeter in an AC current or AC electricity, the fact that it goes backwards and forwards, you actually see the needle in the ammeter go backwards and forwards as well. So that's what we have there. Alright, so that gives us a nice little summary endpoint to the what electric current is. So we talked about current as in the flow of charged particles. We also call them charge carriers. So current carriers can be positive or negative. In an electric current, we usually refer to it in terms of electrons, but obviously you have the positive density moving along with it. The units in measuring current is charge over time, okay, and the units to the units for current is amps. And so that's pretty much it. It really just to tell you, how electricity occurs. How do we produce an electric current? We need a good conductor, and that conductor needs to be connected in a loop. Okay, so hopefully that was useful for you. This video is ending at this point here. Obviously there is two parts to this lesson, which next bit we're going to be talking about is the basic concepts of Ohm's law. So follow on with the upcoming video, and hopefully you'll find it just as useful as this one.